8,000 years ago, human beings didn't have a sweetener aisle. If you wanted a hit of quick energy, you had exactly two choices: chew on raw, fibrous tropical grasses, or scale a sheer cliff face to steal honey from wild bees. In the natural world, sweetness was an incredibly rare resource. It was geographically isolated and always bundled with other biological matter. Maple sap is heavily diluted by water. Dates are packed with dense, insoluble fiber that refuses to dissolve in liquids. Ancient cultures treated this rare biological sweetness as an object of immense power. The Egyptians used wild honey as currency and sealed it inside royal tombs to sustain pharaohs in the afterlife. When archaeologists opened the tomb of King Tutankhamun, they found jars of honey that were still edible after 3,000 years. Contrast that scarcity with the modern grocery store. Today, we are surrounded by an overwhelming, highly specialized selection of shelf-stable sweeteners, from pure white crystals to dark molasses and perfectly clear liquid syrups. This massive variety is a physical archive. It is an 8,000-year timeline of human technology, tracking our progression from foraging raw biology to engineering synthetic chemistry. This timeline is locked into the start of the spectrum with the first major technological leap: thermal reduction. Humans discovered that applying intense heat could boil away water and concentrate faint plant saps into dense, stable calories. Indigenous peoples in North America mastered this by harvesting the watery sap from maple trees. Raw sap contains only 2 to 3% sugar, so it takes roughly 40 liters of sap to produce a single liter of syrup. Boiling down that massive volume triggers Maillard reactions, chemical changes that create deep, caramelized flavors that do not exist in the raw plant. We see the exact same thermal logic applied across ancient India and Southeast Asia. Farmers boiled sugarcane and palm juice in massive vats until it evaporated, pouring the thick paste into molds to form solid yellow blocks called jaggery. These early reduced sugars were unrefined. They were dense, earthy, sometimes crumbly blocks that held on to all the natural minerals, trace compounds, and robust flavors of the original crop. Fire allowed early societies to extract new flavors and preserve critical calories for the winter. But at this stage, the resulting sweeteners were still strictly bound by the biological limits of the crops themselves. The next leap: mechanical separation. Engineers discovered how to isolate physical components. By spinning raw juice in early centrifuges, they split the material. One path yielded bright, pure sucrose crystals. The other drained heavy minerals into a viscous, dark pool known as molasses. The ability to isolate pure white crystals created an incredibly valuable global commodity. The intense European demand for clean, neutral sugar directly drove the establishment of massive plantation systems in the Caribbean and Brazil, relying entirely on the brutal exploitation of enslaved African labor. Meanwhile, the dark liquid byproduct of that refinement process, molasses, built its own massive industrial economy. It was shipped to distilleries to produce rum, forming the backbone of the Atlantic triangular trade and filling gigantic storage tanks in industrial port cities. The scale of this industrial stockpiling became lethally clear in 1919. A massive storage tank holding 2 million gallons of molasses suddenly burst in Boston, sending a sticky wave crashing through the streets at 35 miles per hour, destroying buildings and killing 21 people. As production grew into the 20th century, white sugar companies wanted to ensure their refined crystals dominated the market. Brands ran aggressive marketing campaigns, publishing magnified images of harmless microbes naturally present in molasses, intentionally making them look dangerous to terrify the public away from partially unrefined brown sugar. Mechanical separation took sweetness completely out of its local, biological context. It turned a regional food staple into a stripped-down, highly engineered, and aggressively marketed industrial ingredient. That engineering leads directly to the far right side of our timeline. By the 20th century, the food industry abandoned sweet plants entirely, instead chemically extracting starches from mass-produced corn. Inside modern factories, technicians apply precise blends of acids and laboratory-engineered enzymes to break those complex corn starches down into simple sugars like glucose. The result is corn syrup, a perfectly clear, thick liquid that dissolves effortlessly into a flawlessly smooth surface. In the 1970s, chemists took this process further. By treating that syrup with additional enzymes, they converted some of the glucose into fructose. This created high fructose corn syrup, an intensely sweet, incredibly cheap liquid that quickly dominated the soft drink and processed food markets. These chemical syrups were engineered to solve mechanical problems on factory floors. Corn syrup functionally blocks sugar crystals from forming together, ensuring mass-produced caramels and candies stay smooth on the shelf for months. At this stage, sweetness is completely removed from nature. It is molecularly assembled to dictate the exact texture and shelf life of modern food. This entire technological history is hiding in plain sight. When a modern baker opens their pantry to make a dessert, they are choosing which era of human engineering they want to apply to their food. Take a look at this microscopic view of traditional brown sugar. Because it still contains molasses from the separation era, it retains a chemical property called hygroscopy. It physically pulls in and traps water molecules from the air, which is exactly why it keeps a chocolate chip cookie dense and chewy. If you're trying to make a perfectly smooth fudge, you reach for the industrial chemistry of corn syrup. Those long, irregular molecules physically wedge themselves between the uniform sucrose crystals, breaking up the grid and preventing the fudge from turning into a grainy, hardened mess. When a cook needs a clean, stable structure, like a crisp meringue, they rely on fully refined white sugar, delivering pure, structural sweetness without introducing any competing flavors or heavy moisture. The jars and bags lining the baking aisle map an 8,000-year quest to harvest, extract, and manipulate the chemistry of our food.